Hi, this is Sandeep. I am here to give a presentation on analysis and design of a retaining wall or main project. My batch members include Lohit Reddy, Nagarish, Pawan, myself and Mahesh. Coming to retaining wall, a retaining wall is a structure which is used to maintain good surfaces at different elevations on either side of it. The material which is retaining wall is called backfill, and the top surface may be top surface of the backfill may be either horizontal or vertical. The failure criteria for the retaining wall was first initiated by rank. Coming into a common terminology, a key is provided at the joint of the stem and the base. The ground level is the surface which is backside of the retaining wall. A drainage is provided at the base of the retaining wall. In the ground level to the left side is the depth at which the retaining wall is placed below the ground. Types of retaining walls. Retaining walls are classified according to their mode of resisting the earth pressure, and they are classified as gravity walls, cantilever walls, of which are two types, T-shaped and L-shaped, counterfort retaining walls, and buttress retaining walls. Here you can see the picture of the types of retaining walls as classified as gravity retaining walls, T-shaped retaining walls, L-shaped retaining walls, counterfort retaining walls, and buttress retaining walls. Now coming to the cantilever roll, which we incorporated in this design process for the backfill, they are made from internal stem of steel reinforcement and cast in place concrete. It is often in the inverted T-shape shape. These are the following important considerations which were taken before the design. First step is before starting of construction. But first step is to check with the local authority if planning is required. The drainage is also important aspect of a retaining wall. This is our site where the retaining wall is located. Now, before the start of designing of the retaining wall, we first analyze the existing structure, that is analyzing the backfill. To analyze the backfill and to evaluate the properties of the backfill, I have conducted three different tests. They are standard compaction test, which is used to know the dry density and the optimum moisture content. Dry test test to evaluate the C5 parameters of the soil and backfill, and sand replacement test to evaluate the bulk density of the soil. With these laboratory tests, we analyze the wall for different conditions like sliding, overturning, tension failure, and also compression. Now, lateral earth pressure. It is a function of type and amount of the wall movement, shear strength parameter of the soil, drainage conditions of the backfill, which are of either cohesive or non-cohesive, and unit weight of the soil. Three conditions of lateral earth pressure generally, as we know, are at rest earth condition, where the wall is rigid and unyielding, the soil is in a state of a rest, and there are no deformations and displacements. And the earth pressure at this state is known as the earth pressure at rest. Next, the active earth pressure. This earth pressure exists when wall moves away from the backfill, and it is a minimum lateral earth pressure. It is given by gamma z into 1 minus sin phi by 1 plus sin phi. And the passive earth pressure, it occurs when the wall moves towards the backfill. The formula for this is given by gamma as gamma z into 1 plus sin phi by 1 minus sin phi. Now, lateral earth pressure at rest is derived as the following, and the value it is given by Rankine, and the value obtained is of gamma k naught into gamma h square, and it is the total thrust acts at a distance of h by 3 from the base. Surcharge has been in case if there is any surcharge, then the formula changes into k naught into qh plus 0.5 gamma h square k naught. In the presence of water table, the different triangles are being considered for different types of loading or different soil pressure and also the water pressure, and based on that, the formula is evaluated as k naught gamma h square plus 0.5 gamma h square into k naught plus k naught into q plus gamma h1, where q is a surcharge, and k naught into gamma sat into h square by 2. Gamma sat is a saturated unit weight, and k of gamma h square. Now, Rankine's passive earth pressure. This pressure occurs when the wall moves away towards the backfill, and it is given by 0.5 kp into gamma h square plus 2ch into root kb, where c is the Coulomb's active earth pressure. In this consideration, triangular wedge is considered. The forces acting are transformed or interpreted on a triangular wedge, and the active earth pressure evaluated with this triangular wedge. Similarly, the passive earth pressure is also evaluated in the same procedure. These are the wall movements for passive condition, which gives the failure criteria. Now, coming to the test conducted on the backfill to evaluate its properties, the three important tests we have conducted to evaluate the properties are standard compaction test, direct shear test, and sand replacement test. Standard compaction test. In this test, we determine the dry density at which the maximum dry density and also the optimum moisture content at this dry density. The optimum moisture content is obtained from a graph drawn between the dry density and sample is in this the sample is compacted in 3 layers of 25 blows of each. Here are the calculations for which we got the optimum moisture content as 14.28%. Now the next is a bulk unit weight. Bulk unit weight is defined as the weight of the soil mass per unit volume V. This can be evaluated by using two tests, sand replacement test and core cutter test, and we have conducted sand replacement test in our field density test by sand replacement method. The main objective of this test is to determine the in situ density of the natural or compacted soil. Now, by doing the standard compaction test, we got the values of a distributed sample, but by using the sand replacement method, thus the in situ density is we get the in situ density. And the basic principle is to measure the in situ volume of a hole from which the material is extracted and weigh of the in the hole. Apparatus. Here the different kinds of apparatuses are shown in the figure: calibrating container, tray, and also the measuring cylinder. Calibration is done in the following steps. So first, the sand pouring cylinder is filled with the clean sand up to the top of the level, and the initial weight is found out and noted as W1, and which should be maintained as constant. And the sand of volume equal to that of calibrating container is run out of the cylinder by opening the shutter. The observations from this test are like this, and from which we got dry density as 1.58 gram per cubic centimeters. Shear strength. Shear strength is defined as the ability of the rock to withstand the shearing, the maximum shear strength which a material or soil is capable of sustaining. The shear strength can be resolved into cohesion and friction and angle components using S is equal to C plus sigma into tan phi, where S is the shear strength, C is the cohesion, and sigma is the normal stress applied, and phi is the friction angle in degrees of the back. Now direct shear test. It is used to evaluate the C5 properties of the soil or the backfill. The test equipment consists of a metal box which is in which a soil specimen is being placed. The box is split into two halves. A vertical force or normal stress is applied through the metal plate, and the shear force is applied by moving one half of the box relative to the other to cause a failure in the soil specimen. Components of metal box. Here you can see the components of metal box, where the upper half and the lower half separated, and the pressure pads are applied perpendicular to the force. Failure criteria. When the force is applied both horizontally and vertically, then the failure of the soil particles occurs along the shear plane, and the particles slide over each other. The slide or roll past over each other. You can see the failure of a sample in the laboratory. Here we are conducting the experiment, the shear mole, and the failure of apparatus, and the inspection. Here you can see the failure of the sample in particular, and a graph is being drawn between the normal load and the shear stress values obtained from the direct shear test, from which the slope of the line gives the friction angle, and the point at which the line coincides the y-axis gives the y-axis or shear stress axis gives the cohesion, for which we got the cohesion as 0.3616 and friction angle as 29.57 degrees. Calculation of active earth pressure. After obtaining the values of the cohesion and friction angle, we calculate the active earth pressure. and also passive earth pressure. Active earth pressure is given by Rankines as Pa is equals to gamma h into Ka minus 2c into root Ka, for which the height of the retaining wall is 6 meters, for which we got the active earth pressure as 31.055 kN per meter square. Now total active earth thrust is given as, it acts in the form of a triangular wedge with a 0 at the top and Ka into gamma h at the bottom, and it is given as a formula here you can see, and we got a value as 92.018 kilonewtons. Calculation of passive earth pressure. Passive earth pressure is calculated by using the formula derived by Rankines, which is given as Pp, which is active earth pressure, is equals to gamma h into Kp, which is a coefficient, Kp is a coefficient of earth pressure, plus 2c into root over Kp, where c is a coefficient. Now the height of the retaining wall is 6 meters. Failure of retaining walls. Now coming to the failure of retaining walls, the major failure criteria is a failure by overturning. This overturning failure is caused when the overturning moments exceed the resisting moments of the retaining wall. Here you can see the different types of forces acting on the retaining wall and the distance of their action of the overturning moments is given by this formula, where Pa is the active earth pressure, which is calculated before, and the resisting moments are the moments which were created by the own weight of the retaining wall. Different components were used in the W1, W2, W3, W4. W1, W2, W3 constitute the weight of the retaining wall, and W. The next major criteria of failing is by sliding. Sliding failure occurs when the resisting forces of the retaining wall were exceeded by the horizontal forces acting upon it. The force of resistance F is given as F is equal to mu into sigma W, where W is the weight of the vertical forces to summation of total vertical forces of the retaining wall, and P is the horizontal pressure. A minimum factor of safety of 1.5 is used. What if the failure happens in sliding? Then in order to overcome this failure, a shear key is provided. When the shear key is provided, a passive earth pressure acts on the the next failure condition is the base pressure failure. This occurs when the pressures at the base exceed the bearing capacity of the soil, especially the pressure at the toe. With the pressure at the toe is maximum, and this pressure should be within the limits of the safe bearing capacity of the soil, and the pressure at the heel must be greater than 0, and if it falls less than 0, if it is a negative value, then the tension failure occurs at the heel. So in order to maintain it greater than 0, the eccentricity, that is a distance of action of the resultant from the. Now, if sigma W is the sum of all vertical forces and Pa is the horizontal active earth pressure, the resultant R will strike the base at a distance from the middle point of the base. Net moment sigma m is equals to W1 x1 plus W2 x2 plus W3 x3 divided by in W3 x3 plus PA into h by 3 at a distance of h by 3 from the base. Eccentricity is given as b by 2 minus x. Here you can see the pressure distribution at toe and heel. Now the bending failure, this can be of three types, in which stem AB and heel slab BC and toe slab DB are considered. The first stem AB, it bends as a cantilever with tensile face towards the back wheel. The critical section will be at B, where crack occurs if not properly reinforced. Coming to the slab BC, it has a net pressure downwards and will bend as a cantilever having tensile face upwards with critical section of B. Hence, reinforcement is provided at the upper surface. Toe slab DB. The net pressure at toe slab BC acts DB acts upwards and hence reinforced at bottom face. The thickness of stem, heel slab and toe slab must be sufficient to withstand the compressive stresses during bending, and also the economy must be considered. Coming to the design of retaining wall. The various dimensions of the retaining wall should be so proportioned that various failure criteria discussed above are taken care of. The design of retaining wall consists of following steps. First step include the depth of foundation. Second step, dimensions of the base and stem are found out. The stability of the wall is analyzed for the dimensions, and the overturning and sliding failure conditions are analyzed, and also the base pressure failures. And now here you can see the proportioning of retaining wall. Approximate dimensions are chosen in the retaining wall, and the stability is checked. The section is changed if it is undesirable from the stability or economy point of view. Preliminary dimensions. The tentative proportions of cantilever retaining wall may be obtained based on experience and optimization studies. So the base width is set between 0.48 h to step 1. Depth of the foundation. The unit weight of soil gamma is equals to 15.489 kg per meter cube, which we obtained from the bulk density or the sand replacement test, from which the minimum depth of foundation is found out using the formula given, and for which we got it as 1.81 meters. Now to accommodate the base thickness of the slab, we took it as a 2.8 meters below the ground. Hence the retaining wall height is given as 8, for which we obtained is 8.8 meters with a 6 meters solid present and 2.8 meters below the ground. Now design constants for this is, because we took the M20 concrete and Fe 415 steel, for which the design constant, that is XU max by D is 0.479, and now used to dimensions of the base and stem. Now the dimensions of base are considered from stress conditions and also from the sliding considerations. The base width B should be so chosen that ratio of the toe slab to the base width should be such that the pressure that toe does not exceed the safe bearing capacity. So by assuming the unit weight of concrete and soil equal to 1.1 gamma, we get the W as total weight of retaining wall as W is equal to 1 minus alpha into B into H into 1.1 gamma B H into 1 minus alpha. From the base width is evaluated by using this formula, and alpha is the ratio between the B. Now from this formula we got alpha as 0.183, and the base width B is equals to 4.17 meters. From the base width from the sliding considerations is by taking a factor of safety 1.5, we got it as 5.11 meters, 5.28 meters, and hence no, we got it as 5.11 meters, and which is in the limit of 0.6 h, which is 5.28 meters. So 5.11 meters is accommodated as a length of the base. Now the width of the toe slab. The width of the toe slab is given as alpha into B, where alpha is 0.183 and the base width is 5.11 meters, from which we got it as 0.94 meters. Thickness of the stem is arrived by using the formula as the by using the maximum moment at B and the moment effective and the moment. The design of cantilever can be uh, understood from this figure, where the different steps are being given of the calculation of moments. Now next is the stability of the wall. Stability of the wall is being ensured by the total vertical forces from weights, from which W1 is the weight of the rectangular portion of the stem and W2 is the weight of triangular portion of the stem. W3 is the weight of the base slab and W4 is the weight of the soil and the heel slab. For which we got the values as following, and with the and from which total resisting moment MR is equal to 1853.09 kilonewton meter. Overturning failure. Overturning failure. To analyze overturning failure, we get that pressure PE is calculated as K into gamma H square by 2, from which we got 203.36 kilonewtons. It's a total earth thrust, and the overturning moments are being calculated as 596.52 kilometer meter, from which we got the factor of safety against overturning as 3.1065, which is greater than 2, and the structure is safe against overturning failure. The next failure consideration is the slide. Stability against the sliding. Different uh, methods are used to ensure the safety against sliding. They are as follows: like use of base key to increase the passive resistance against the sliding, or the shear key, or we can increase the base slab thickness of the base slab, and also by providing a deadman anchor and the upstream side and pressure distribution. The net moment sigma m is calculated as 1256.57, and the distance of application is 1.926 meters from the toe slab. Eccentricity is obtained as 0.69, which is less than b by 6, and hence there is no tension failure at the heel. Now the pressure at toe is being calculated as the value is obtained as 212.81. The pressure distribution is given by the following figure, in which the pressure at the toe slab is given as 212.816 kN per meter square, and the pressure at the junction of toe slab and the stem is given as 179 is obtained as 179.55, and the pressure at the junction of heel slab and the stem is obtained as 86.49, and the pressure at the heel slab is 32 kN per meter square, all dimensions kN per meter square. The next step is the design of toe slab. Here the following steps are used in the design of toe slab. First, the ultimate bending moment for 1 meter width of toe slab is being calculated, and the weight of the weight of soil above toe slab is neglected. The two forces considered are upward soil pressure and the downward weight of the soil. A reinforcement is provided accordingly, and distribution is also provided. Development length check and shear check are being done to ensure the safety. Here you can see the calculations of the design of the toe slab, from which we got a depth of 255.486 mm. So to ensure the safety, we took as a 500 mm effective depth. 500 mm, the effective depth of 440 mm, so that 60 mm cover can be provided, and thickness can be reduced to 400 mm at the edge. For this, area of steel required is 1475.94, and so as and hence we provided reinforcement of 12 mm for 12 mm diameter bars. Development length obtained is 564 mm, which is less than the maximum value, hence it is safe. It is less than the available length, hence it is safe. Now the next is the design of heel slab. In this, the ultimate bending moment for 1 meter width of heel slab is being calculated, and the three forces considered: upward soil pressure, downward weight of the heel slab, weight of the soil above heel slab. and the main steel and distribution steel are accordingly provided, and a check for development length are being considered. The calculation for this include the total weight of soil, which is 446.36. The total upward soil reaction is 211.5. It is acting. Now this is below this is under reinforced section. We use this formula. We use the formula as given to evaluate the area of steel, which we opened as 4330.25 by using the 20 bars of 14 numbers at the 70 spacing. The reinforcement is provided. For the distribution reinforcement, 12 diameter bars are used. Now, the shear stress is calculated as 0. It's calculated for which we got as 0.4605 Newton per mm square. From IS 456 table, we got the area of steel AST by BT. There is a percentage level 1.08, for which the shear stress value is 0.638. Now, this value is greater than the value of the shear stress for this rectangle for this design. Next is the design of the stem. In this, the maximum factor bending moment on the stem due to lateral earth pressure is being calculated. The calculated bending moment must be less than the limited bending moment. M is calculated as 0.87 Fi AST D into 1 minus Fi AST by FCK BT. And distribution still for development length and shear is being done. Now the basic is the since the wall is in the design of shear key, since the wall is unsafe and suddenly shear key is being designed, and the shear key will be provided below the stem at a depth of let us assume the depth should be of 5 meters, and by taking a minimum factor of safety of 1.5 and calculating the passive pressure acted upon the retaining wall by the soil wedge being surrounded by the stem, we get minimum depth or width is 119 meters. So in order to ensure more stability, we took it as 300 mm, and the depth of key is 300 mm by 300 mm dimensions of the shear key. Now we have done the structural detailing of this design in the AutoCAD structural detailing 2013, and reinforcement is provided manually. For in this design, in order to consider the conclusion. Hence, by taking different considerations into view, a design procedure is adopted, and in this we adopt the one which is more economic in cost and also which ensure more stability and more service life. The shear key which is provided in the design 3 greatly increase the frictional force of the retaining wall by passive earth pressure, which increases the stability of the retaining wall. All drawings were performed in AutoCAD structural detailing 2013 along with the reinforcement details of the retaining wall. By designing the retaining wall manually and incorporating the software for designing the project is a good example of combined manual and technological success. Thank you.